Good morning. This is chapter 6. We're talking about uniform circular motion and gravitation. This has a lot of applications in the world around us, and we'll hit the high points. So when we talk about this, what we're going to do is look at our linear equations and our linear concepts and convert them to a rotational point of view. So in this section, sometimes it's important to measure our angle not in degrees, but in radians. I know that when you had math class, you probably used pi. You might say that it was 1/4 pi radians. Well, for us, we're going to take pi and turn it into 3.14 and go ahead and calculate it out. So don't give me answers as fractions of pi, all right? So now that we've straightened that out, let's move along. So we're going to measure in radians, not in degrees, at least briefly. We're going to do that. I promise we won't overdo it. The relationship between the angle of rotation and the distance it's traveled along its edge or its circumference is given by this equation. Delta theta is equal to delta S divided by R. Delta theta is the angular displacement. Delta S is the distance along the rim or the radius. And R is the radius of our circular path. Normally, we think of radians as being unitless. I will probably always say them and in fact write them down, because when I was taking math, that's what we did, and I don't want you to get them confused with anything else. So just to make sure that we all know what we're talking about, I'll write out radians rather than just give you a number. So one complete revolution around a circle is the same thing as 2 pi radians. So that would be 2 multiplied by 3.14 radians, which would give us 6.28 radians, and is the same as 360 degrees. You need to know that 360 degrees is equal to 6.28 radians, because we're going to have to convert from degrees to radians along the way at some point in time. So you need to know that relationship. 360 degrees equals 6.28 radians. And if you can't remember 6.28, I stick with the same as 2 pi, and I know that pi is a button on my calculator, but I also know its value. So let's look at our drawing. Delta S is the green part of the rim. R are these blue lines coming out, and delta theta is this angle that's encompassed by it. You should notice the relationship between theta and S, so between angular measurements and linear measurements. So linear would be on the outside edge, delta S, angular would be delta theta. We've got that delta theta is equal to delta S divided by R. So we have the linear measure, that was delta S, divided by the radius, that will give us the angular measure. And this is going to be true for all angular measurements that have a linear correspondence to them. So angular velocity would be linear velocity divided by R. Angular acceleration would be linear acceleration divided by R. So as we go along, that relationship is always going to hold. All right. So angular velocity is given by the equation delta theta over delta t is equal to omega plus omega 0 divided by 2, where omega, this is the Greek letter lowercase omega. It looks a little bit like sort of a roundy W. It looks like a roundy W. Come on, come down. We're going to draw something just for a second. I find that a lot of you don't do so well drawing your Greek letters, so I'm going to take a minute and do that. So omega, you come down and curve around, and usually there's a little loop in the middle and it comes back. And it's a small letter. It's the same size as a lowercase w. But that is, obviously I drew it large because that's the only way I can on this computer. But that's what a lowercase omega would look like. So you start up high like you're doing a script W, and you come down. Usually there's an inside loop and down and then up again. All right, kind of like a 3 taking a nap. Again, lowercase omega. All right, so we will ditch that for right now and move along. So delta theta over delta t is omega plus omega 0 over 2. And remember I said it was going to be angular is equal to linear divided by r. Well, we could look at it the other way, that linear equals angular multiplied by r. So here we have that v bar is equal to r times omega bar, and v equals r times omega. So v is linear velocity, omega is angular velocity, r is the radius. Angular velocity is going to be measured in radians per second, which is the same thing as 1 over seconds, which is the same thing as seconds raised to the -1 power. Angular acceleration. Angular acceleration is symbolized by the Greek letter lowercase alpha. And alpha looks like the way they used to teach us to draw fish when I was little. So again, it's the same size as a regular A, but you come down, make a loop, come up, and then down again. So it's some version of that. And again, mine's not very good. Let's see if I can do another one that's a little better. It is really hard for me to draw. That one's maybe a little better. The circular part could be a little fatter. So, you know, somewhere in between the two, but you usually start with the high part of the loop. So start with the top leg, come down, loop up, come down and up and over and down again. All right, you're gonna have to know how to draw these, so you wanna practice. All right, so angular acceleration is equal to change in angular velocity over change in time. You'll need to know this equation. So alpha equals omega minus omega 0 over delta t. Angular acceleration is measured in radians per second squared, which, because a radian's not technically a unit, is the same thing as 1 over second squared, or seconds to the -2. And again, if we look at our relationship between linear and angular velocity, linear is equal to r times angular, so A equals r times alpha. A equals r times alpha. All right, frequency and period. We're just hitting all the high points. So the frequency is the number of complete revolutions per second that an object makes when traveling a path. We can think of the frequency in terms of a pendulum's path. So a pendulum swings out and back. When you end up back where you started, that's a complete revolution. Or if you're going around a circular track, once around is a complete revolution. Normally we symbolize frequency by a lowercase f. We will measure it in hertz. Hertz are abbreviated, capital H, little z. And it's the same thing as 1 revolution per second, which is the same thing as 1 cycle per second. Now there is a relationship between frequency and period. There is a relationship between frequency and period. Period is the time required for 1 complete revolution, and we symbolize it by capital T, and it measures time, so it's in seconds. And the period will equal 1 divided by the frequency. Period equals 1 divided by the frequency. So period and frequency are inversely related. There's a relationship between frequency and angular velocity. F is equal to omega divided by 2 pi. Why 2 pi? Well, 2 pi is once around the circle. So 1 revolution around the circle So your angular velocity divided by 1 revolution will give you the frequency. All right, so some practice stuff for these problems related to what we've just talked about can be found at the end of chapter 6. Now, let's look at this. We want to compare the linear equations to their angular equivalents. We are supposed to already know these linear equations. We know that delta x over delta t is equal to v plus v0 over 2. If we write that as an angular equation, all we have to do is translate. X's become thetas and v's become omegas. So instead of v bar, we have omega bar. Instead of delta x, we have delta theta. Delta t stays delta t. V becomes omega. V0 becomes omega 0. And 2 is just 2. So it's really easy to write the angular equivalent if you know the linear velocity equation. If you know the linear acceleration equation, a is equal to v minus v0 over delta t, then alpha is going to be omega minus omega 0 over delta t. The distance one, oh, I didn't write it as delta x. I am so sorry. It looks like I screwed it up, didn't I? All right, we can fix it. We've gone to these symbols and I just forgot to change it. But I think I can make it work. All right, and on this one, I think I can make it work. All righty, except now my delta is not blue, but we'll fix that. I just looked right over it. All right, so all we've done is translate. You ought to be able to do that. If I give you a made-up equation, a pretend equation, you still ought to be able to translate it because you ought to know that omega is the same thing as v, theta is the same thing as x, alpha is the same thing as a. So if I give you an equation with v's and x's and a's in it, you ought to be able to rewrite it with thetas and alphas and omegas in it. So let's do an example. Put some of this to use. I think we can move that up. All right, so suppose we have a record and it starts from rest and reaches 45 RPM in 2 seconds. What's the angular acceleration? All right, I know that most of you don't play records or even CDs, that your music is in the cloud. But there are lots of things in the real world that still go round and round. So makes me think of the wheels on the bus. So we still need to look at RPMs. So we know that V0, it starts from rest. So we know that V0 is the same thing as omega 0 equals 0. Nothing's moving. Omega, our final velocity, is 45 RPM and delta t is 2 seconds. And then want the angular acceleration. Well, we know that A is equal to delta V over delta t, so alpha is delta omega over delta t. We also know that 1 minute is 60 seconds and that 1 revolution is 2 pi radians, or if you want to, you could call it 6.28 radians. The very first thing you do when somebody gives you a number in RPM, unless they want the answer in RPM, is convert. So our first step is to convert. We want to convert RPM into radians per second. RPM stands for revolutions per minute. It is a good idea to write that out because you're going to get busy and screw up because you're going to forget that R means revolutions and not radians. So let's see how I convert. 45 RPM, I rewrote it as 45 revolutions over minutes. I want to get rid of the minutes, so minute goes in the numerator. I need seconds to be left. So seconds go in the denominator, and I know that 1 minute is 60 seconds. So this first part will convert minutes into seconds. And then to get rid of the revolutions, I need revolution in the denominator and radians in the numerator. We know that 1 goes with the revolutions and 2 pi goes with the radians. So I have, going across the top, 45 multiplied by 1 multiplied by 2 multiplied by pi equals, you'll get a number. And you divide that number by 60 because 60 multiplied by 1 is still 60. Revolutions cancel revolutions, minutes cancel revolutions. We're left with radians per second, and the number is 4.71. If you don't get 4.71 when you do this calculation, I need to help you with your calculator. So after we've done our very first thing, converted the number in RPMs to radians per second, now we can find alpha. So alpha is delta omega over delta t, so that's omega final, that 4.71 radians per second, minus our starting angular velocity, which was 0, divided by the time, which was 2 seconds, and so alpha is 2.356 radians per second squared. You ought to be able to do a problem like this on a quiz. They are really easy, and I ask it a lot. I'm especially concerned that you can convert RPMs into radians per second correctly. So practice. You have an example, and there'll be some practice problems on the study guide. All right, things going in circles. That gets us to centripetal acceleration. So objects in uniform circular motion have an acceleration. The magnitude is going to be constant, but usually it's the direction that's changing to produce that changing velocity. So when you go in a circular path, even if you're going at exactly 50 miles an hour around the circle, you have to continually change your direction, which means you're continually changing your velocity, even though the speed is the same. It stays 50 miles an hour. So anyhow, it requires a centripetal acceleration. That's the acceleration that keeps an object in circular motion, and it is directed inward towards the center of the circular path. Some people confuse this with centrifugal. Centrifugal has an F in it, and it is the equal but opposite force. When you think of centripetal with a P and centrifugal with an F, they form action-reaction pair forces, and we'll talk more about that later. But centripetal acceleration pulls you in. The formula for that would be A sub c, the sub c meaning centripetal. A sub c is equal to v squared over r. And it's an acceleration, so it's measured in meters per second squared. We can also write it in terms of angular velocity, where, in terms of angular velocity, where A sub c, our centripetal acceleration, we said it was v squared over r, but v squared would be r squared omega squared. So one of the r's will cancel, and we're left with r omega squared. So here's a way to take angular velocity and a radius and get centripetal acceleration out of it. So some problems to help you practice with that. Let's look at centripetal force. I said we'd get to this. So centripetal force is the force that keeps an object going in a circular motion. It is inward directed, and it is given by the equation F sub c is equal to mv squared over r. So centripetal force measured in newtons is equal to the mass, m is the mass, v is the linear velocity, and r is the radius of the path. You can see I didn't define all of those because I'm hoping by now you recognize that that's what they are. But if not, jot it down. M is the mass, of the object going in the circular path, and v is the velocity that it's traveling in, so the speed really, and r is the radius of the path. You should notice that the larger r is, if r gets bigger, 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 but your velocity stays constant, so maybe you've got 4 circular paths, one is a kilometer across, the other one is 2 kilometers across, and the next one is 3 kilometers across. R goes from 1 to 2 to 3. And if your velocity is 100 meters per second on the first one, then, and you keep it 100 meters per second on the second and the third, as your track gets larger and larger to maintain that same velocity, it takes less and less force. So it's easy to make a big, wide, sweeping turn, not so easy on a little tight one, which is why exit ramps tend to be larger in diameter. They tend not to be super tight, and why they have, one of the reasons why they have speed limits on exit ramps. I've told you about centrifugal force earlier, so let's get back to it. So centripetal with a P pulls you in, P for pull. Centrifugal with an F is the one that is outward directed. It forces out. It doesn't act on the object, it acts on the restraining device. It acts on the restraining device. If you want to think of, you tie a rock to a string and twirl it over your head in a circular path, then the rock is being pulled in by the string, but the string is being pulled out by the rock. If you think about it, this is related to automobiles and how we drive. Let's talk about riding in a car. If you are negligent and don't put on your seatbelt, you might feel yourself swaying around as a car takes a curve. Or if you've thrown your books in the back seat instead of on the floorboard, they're not going to stay stacked up when you make a curve, they're going to slide. And in fact, if you turn left, they slide right. And the reason is, a lot of people say, oh, the centrifugal force pushes them. No, it doesn't. So what's happening with you riding in a car or the books or anything else you've got that's not securely strapped down is that inertia keeps the object going in a straight path, and the object, if the object is in, say, an automobile, the bottom of the object turns with the car, but the top of the object wants to continue in a straight line. So if it's you not wearing your seatbelt, your upper body goes in a straight line, but if you're making a left turn, your lower part of your body goes left. Your sensation is not that your lower body went left, but that your upper body got pushed right. Or with the books, they try to go straight, but you pulled the bottom out from under them. So they don't really fall to the right so much as you move everything left. So friction is the force that allows cars to make turns on flat roads. It is the frictional force between the tires and the road. And what that does is that friction grips the tires, and that allows the tires to reposition and turn. If you don't have friction, the tires can't get a grip, and so you have no control over your motion. Again, think of a wet road or an icy road. I hope you haven't tried to drive on one, but all it takes is once for you to know, whoops, this is not the way to go. Centripetal force is the name we give any force that pulls you into a circular path, no matter where it comes from. It can be because of friction or gravity, or I can tie you to a string and do the old heave-ho and pull you in. And I would be supplying the centripetal force. So centripetal force is just a name for forces that pull you in a circular path, but they have to have some source. And again, on a flat road, that is friction. So we know on a flat road, a car will make a turn when the static frictional force between the tires and the road is greater than or equal to the centripetal force calculated for how fast you want to go and how big is the circular path. If you don't have enough static friction, your car is going to skid. So in our drawing, we've got the weight coming down, the normal force goes up, and if this car is turning left, centripetal force will turn left and point left. So weight down, they're using a capital N for normal force. We would use an F sub N. I should have changed it. I'm sorry. And centripetal force is the same as the frictional force, so it's mu times the normal force. We'll work with that. All right, here's an example, and you have most of it written out on your paper because I'm not going to ask you to recreate it. I just want you to see where the horizontal and vertical force equations come from, and I want to talk about the final result. So we know a car has a mass m, a radius r for our circular path. Coefficient of static friction is mu sub s. We're going to make a left turn. We're trying to find how fast can we go. Oh, I'm sorry. This isn't really appropriate for us. So formulas, F equals ma, W equals mg, the static frictional force, and the new one, centripetal force, mv squared over r. You need to learn the new one. F sub c is equal to mv squared over r. So horizontal and vertical force equations come from the diagram. Weight comes down, normal force is up, centripetal force is pulling us left into the circular path, and we've said it's going to be static friction. So F total in the x direction is m times a sub x equals centripetal force, but that we said was the same as the static friction. Vertical forces add up to 0 because the car doesn't levitate, the car doesn't sink, and it'll be equal to the normal force going up and the weight coming down. All right, we have a series of steps to solve for little v. It's not really important for you to remember how it got there. We want to talk about the end result, but I did want to provide them for you. So we find the weight and then the normal force and then static friction and the centripetal force, and then we find the velocity. What is important is that we talk about the velocity. The velocity is going to equal the square root of mu sub s, so that was the coefficient of static friction, multiplied by little g. Remember, little g is 9.8 meters per second squared, multiplied by r, which is the radius of the curve. So take those three things, multiply them together, get an answer, take the square root. What is significant is that velocity does not depend on the mass, but it does depend on the radius of the circle. It is independent of the mass. The mass cancels out along the way. If it did depend on the mass, we would have to have a different velocity for a Ford F-150 pickup truck compared to my Toyota Camry compared to somebody's Fiat. And we don't. We do have different speeds on exit ramps sometimes for trucks compared to automobiles, but that is not so much about the mass as it is the high center of gravity. A truck has a tendency to be unstable in tight turns. We're talking trucks that carry cargo, because the center of mass is up so high, and so they have a tendency to tip over. And we'll talk about that later in another chapter. So this is an equation we need to be able to use, but you don't need to memorize it. I'll provide it for you on the test. You just need to know where it's applicable. And it's applicable for cars on curves, flat roads. Cars on curves, flat roads. All right, so why do we slow down on a rainy day? Well, we slow down because the coefficient of static friction is reduced. The same would be true for an icy road. We slow down because you don't have a whole lot of friction between your tires and the road. So you would be given that V equals square root of mu s times g times r on the test. You don't have to memorize that. You just need to know how to use it. So let's look at how we use it. We have an example. What speed would a 2,000 kilogram car safely take a curve if the coefficient of static friction is 0.1 and the curve is flat and the radius is 10 meters. So mass is 2,000 kilograms. You'll notice there's a space between the two and all those zeros, but no comma. In scientific writing, almost never do we include commas in large numbers because commas can be mistaken for decimal points. And in some places in Europe, the comma is used where we would put the decimal and the decimal is used where we would put the comma. So it can be confusing. So oftentimes we just move things over in groups of 3. So 2,000 would be 2 with the space and then the 3 zeros. So 2,000 kilograms, mu sub s, the coefficient of static friction is 0.1. R is 10 meters. We're going to make up positive. We want to find V. You will be given this equation. You'll also be given another one, so you need to know which one to use. This example has no angles in it, no theta. So this equation has no angles in it, no theta. So this is the one we'll use. The other equation has a theta in it, in case you're wondering. So V equals square root of mu S times G times R. Mu is 0.1, G is 9.8 meters per second squared, and R is 10 meters. Do the math. 0.5, so 0.1 times 9.8 times 10 gives us 9.8 meters squared per second squared. I should have picked a different number from 10 or 0.1. And you'll notice I've got it raised to the 0.5 power. That is the same thing as taking it to the 1/2 power, which is the same thing as taking the square root. It was just easier for me to write it like that. And I wanted to remind you that raising a number to the 0.5 power is the same as taking the square root. So when we do that, square root of 9.8 is 3.13, and it would be in meters per second. Okay, let's put some banking on our curve. So we have a car going on a left turn, but the road is not flat. Think exit ramp. Actually, most curves should be banked a little bit. Some roads are not banked very much, but they ought to be. If the speed limits are high, the higher the speed limit, the more banking you need to have, and you'll see why in a minute. So this road is not flat. It is tilted at an angle theta. So we have the weight coming down. The normal force, remember, makes a 90-degree angle with the surface of contact. So that would be what we would resolve into components. Because remember, you are one with the road. But you are not going to have to calculate that. We're just going to use the end result. So we've got our general statement to help us derive the equations. And again, you're given all of this except the horizontal and vertical force equations. You'll notice that F total X is equal to the centripetal force, which pulls us in. And in this picture, the only thing pulling us in is the X component of the normal force. And in the Y direction, we have that it's equal, the total force is 0, and it's the Y part of the normal force plus the weight. So again, those equations come from the picture. And you can look through the math. You are not required to know it or do it. I'll just give you the end result. So F subs, we find the centripetal force, and that helps us find the X and Y components of the normal force. And then we can plug in and solve for the velocity. And we get that the velocity is equal to the square root of R multiplied by G multiplied by the tangent of the angle theta. And remember, theta is this little angle down here. It's the banking angle. So remember I told you in the previous equation, it didn't have an angle in it, and this one does. So if you have a banking angle, you use the formula with theta in it. If you are on a flat road, you use a formula that does not have theta. So speed is going to depend on the radius of the turn. We've already talked about that. The tighter the turn, R would be a small number, so we go slower. And theta, And so the bigger your banking angle, the faster you're going to need to go. All right. In this equation, there's no friction between the tires and the road. Well, in the real world, we know there's friction. But we're going to assume no friction. And you'll notice in this equation, mass still doesn't enter into the equation. So if we're given the two V equations, the one we had in the previous example and this one, they'll be provided. So let's look at this example. How fast could the car from our previous example take the curve if we now bank in at 15 degrees? So M is 2,000 kilograms, R is 10 meters, theta is 15 degrees. We're going to ignore friction. Up's going to be positive. We're still looking for velocity. But now our equation is V equals the square root of R times G times the tangent of theta. Because this is the version of the velocity equation for cars going on curves that has theta in it. So we plug in. R is 10 meters, G is 9.8 meters per second squared, and theta is 15 degrees. So you will notice that it ends up being the square root of 26.26 meters squared per second squared, which gives us 5.1 meters per second, which is larger than in the previous calculation. Again, I'll provide the formulas, you just have to be able to pick. And here's some homework problems to practice on, and there are also some study guide questions for practice. So Newton's law of gravitation, every object in the universe is attracted to every other object in the universe by a force. That's what helps us when you set down your pencil. That's why it doesn't fly to the ceiling. Gravity is pulling it down. Yay for gravity. I would hate for everything in my life to float. It would make household tasks very difficult. So the equation that allows us to calculate that force is that capital F is equal to capital G. This is not little g, it's capital G. So capital F equals capital G multiplied by, you could call them M1 and M2 or little m and big M, it does not matter. Some books do M1 and M2, some do little m and big M. I think our book must do little and big. As long as you can tell them apart, it doesn't matter. So capital F is equal to big G times little m times big M over R squared. I think I really like M1 and M2, but hey, what are you gonna do? Big G, capital G is called big G. We had little g, that was 9.8 meters per second squared, because we have big G. Big G is 6.673 times 10 to the negative 11 Newton meter squared per kilogram squared. You do not need to memorize that number. I'll give it to you in a list of knowns. This is a statement of Newton's law of universal gravitation, and it's responsible for action at a distance forces. So again, it keeps your pencil from flying around the room. It does a whole lot of things. It's actually responsible for the tides. The water on the surface of the earth is attracted to the mass of the moon, and that shifts the water around on the side of the earth closest to the moon. The end result being that the side of the earth closest to the moon experiences a high tide. The side of the earth at 90 degrees to that will be low tides. And on the back side of the earth shields the water, so it just sort of stays in place, and it ends up being actually a second high tide. So if you have 2 high and 2 low tides a day, it's called semi-diurnal. If you have only 1 high and 1 low tide a day, it's diurnal. The sun does contribute to this process, and the tides are impacted by land masses. Almost always these diurnal, the 1 high and the 1 low, there really is a second high and the second low, but it's so minimal you can barely register it. You tend to find that in places where there's a lot of land mass sort of sheltering things. For example, the Caribbean. All right, so here we have a little graphic. We have the Earth and the sun, and here's a little blob of the water, and the moon is going around the Earth. Spring tides are tides of maximum variation, so the high tides are as high as they can get and the low tides are as low. That would be at new moon and full moon. And again, if you line up your pencil with the Earth and the moon, that's the line the high tides fall on, and at 90 degrees to that would be low tide. So spring tides, maximum variation. If we've got our new moon configuration, this is the Earth, the big circle's the Earth, the little one is the moon, and the sun is the sun. Line up your pencil with the moon and the Earth, that's the line the high tides fall on. 90 degrees to that would be low tides, and again, we're hovering. We are hovering. We're looking down from our giant physics craft. Full moon, the moon is on the other side. And we have, again, line up the moon and the Earth, that's the high tide line, and low tide is 90 degrees to that. Neap tides. Neap tides are tides of minimum variation. The moon and the sun both pull on the water, and so that tug of war, if you will, means that the high tides are not quite as high as they would normally be. They still fall on the line connecting the moon and the Earth. That's still where they are. And low tide is still at 90 degrees to that. So it's at first quarter and third quarter. The moon goes around the Earth every 28 days. So from starting position where you'd have new moon to first quarter is a 7-day cycle. From first quarter to full moon is another 7 days. From full moon to third quarter would be another 7. And from third quarter back to new moon is another 7. So roughly a 28-day cycle. And the Earth rotates on its axis once every 24 hours. So a position that starts out with a low tide, 6 hours later we'll get a high tide, 6 hours after that will be a low tide, 6 hours after that would be a high tide, and you're back again. All this turning, oh my. And here's our third quarter. Again, line up the moon and the Earth with a pencil, and there's your tide, your high tide. Okay, so centripetal forces are also the work of responsible for the moon's orbit around the Earth. The moon is in just the right altitude so it doesn't fly off into space or crash down into the planet. It is in the sweet spot, if you will. And centripetal force is to a large extent responsible for the planet's orbits around the sun. So let's look at an example. Suppose we want to know, does the speed with which a planet orbits the sun depend on the planet's mass? To solve for this, you would set the centripetal force equal to the universal gravitational attraction. So centripetal force is the mass of the planet times its velocity squared divided by r, where r is the radius of the circular path. Universal gravitation would be big G times the mass of the planet times the mass of the sun, the big object we're orbiting, divided by r squared. And so that v squared is going to equal G times the mass of the sun divided by r. So the speed does not depend on the mass of this planet, it depends on the mass of the sun and how far away. And this works for circular paths. Most planets actually don't travel on a circular path. It's complicated. We'll have some numeric problems for this. You need to practice them. So let's look and see how the acceleration due to gravity changes with altitude. At sea level, acceleration due to gravity is 9.8 meters per second squared. In Denver, Colorado, which is a mile above sea level, it's going to be a little less than that. And the top of Mount Everest, it's going to be even less. So as you go up, 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 little g gets smaller, smaller, smaller. Let's see why. So to solve for this one, you set the weight of the object equal to the universal gravitational force. So little w equals F sub g. Little w is the mass of the object times acceleration due to gravity. F sub g is big G times the mass of the object times the mass of the Earth divided by r squared. Notice that the mass of the objects cancel and little g is equal to big G times the mass of the Earth divided by r squared. So if big G is a constant and the mass of the Earth is a constant, the only thing that changes is r. And that ends us. We'll stop, do your problems.